So imagine you're standing at the edge of this massive global shipping port.
Oh, wow. Okay.
Yeah. You look out, and there are just tens of thousands of these heavy steel containers stacked impossibly high.
Right, like an absolute maze of boxes.
Exactly. And cranes are moving them around, trucks are hauling them off. But the entire system relies on a central authority.
Like a port manager.
Yeah. A port manager with a clipboard or, a centralized database telling everyone what is inside those boxes, where they came from, who owns them.
And you just have to trust that manager.
You have to completely trust the clipboard. But what if he didn't have to?
That's the dream, isn't it?
Right. What if every single one of those steel boxes could just magically secure itself, verify its own contents, and then permanently weld itself to the box that came right before it?
Creating a timeline that's physically impossible to forge.
Exactly.
I mean, that completely changes the dynamic of trust in any system. You move from trusting a person or, a central database to just trusting the physical reality of the boxes themselves.
And that reality, that is a blockchain.
It is.
So today, we are ripping past all the tech buzzwords. We're looking straight at the plumbing.
Which is so necessary right now.
It really is. So whether you are prepping for a high-stakes meeting or you're curious about digital economies, or maybe you just want to finally understand how this technology actually works under the hood without getting overwhelmed, this deep dive is custom-tailored for you.
No fluff, just the mechanics.
Exactly. We're using a really excellent presentation deck today. It's from the Blockchain Academy series by G4 People.
Titled How Blocks and Chains Work. It's a great source.
It is. So our mission today is to figure out exactly what a block is, how they link together, and most importantly, why these digital records are considered virtually tamper-proof.
Because people throw the word blockchain around as if it operates on pure magic.
Right. Like it's just this mystical cloud.
Yeah, but underneath all the hype, it's actually a very methodical, strictly engineered mathematical system.
Okay, let's unpack this. Start at square one. What actually is a block? Well, because we used the shipping container imagery a second ago. But when I hear block, I just picture like a chunk of green code floating on a screen. Is it accurate to think of it simply as a digital shipping container?
It's highly accurate, actually. A block is fundamentally just a digital container, but its specific purpose is holding verified transactions.
No.
You aren't putting, random JPEGs or text files in there. You're putting records of value transfer.
So no cat memes. Got it.
All right, no cat memes. And every single transaction inside that container is required to have a very specific set of critical details before the network even allows it in.
Let me guess. It's basically a shipping manifest.
You can totally think of it that way. According to the source, for every transaction, the block records the sender, the receiver, the amount being transferred, and the time recorded.
Sender, receiver, amount, time.
Exactly. Those 4 elements are strictly non-negotiable.
Okay, so once a container is filled with these verified transactions, what happens?
It gets sealed up and added to the broader network.
But wait, a traditional bank ledger does exactly the same thing, doesn't it?
Well, yes and no.
Because it tracks who sent what to whom and when. So how is this digital container different from just like an Excel spreadsheet sitting on a server at Chase Bank?
That's a great question. The difference lies in the concept of a living ledger.
A living ledger.
Yeah. If we think about a traditional database or a spreadsheet, it's highly mutable.
Meaning you can change it.
Exactly. You change a cell in that spreadsheet, the old data is overwritten, and the new data is just there. The past can be edited.
Right, someone with admin access can just quietly tweak a number.
Precisely. But a living ledger means it is a continuous chronological history of value transfers that just grows indefinitely.
So you aren't editing the past?
Never. You are only ever appending to the future.
Okay, I'm visualizing this. But if this block is a shipping container, and it's being added to this massive, ever-growing yard of millions of other containers, we run into a major mechanical problem here. Well, if I want to find a specific transaction, downloading and cracking open every single massive container just to check the contents would crash the network.
Oh, absolutely. It's way too much data.
So how does it handle that?
That is a massive structural challenge. And it's exactly why the anatomy of a block is split into 2 main parts.
Okay.
The source stick breaks this down into the body and the header. Understanding that split is key to understanding how the whole network functions so quickly.
So the body is the heavy payload.
Right. That's where all the actual value transfer data lives, those thousands of transactions.
The shipping manifest we talked about.
Exactly. But the header is entirely different.
The header is the label on the outside of the box.
Precisely. It acts as the identifying metadata, the block's unique ID.
Oh, so the network can just scan the lightweight header to know everything it needs to know.
Right. It reads the block's identity and its place in the chain without ever looking at the heavy payload inside.
That makes total sense. So what's actually written on this label? If I'm a computer scanning a block's header, what data am I looking at?
There are 4 vital pieces of data in the header. First, you have the timestamp.
Which establishes exactly when the block was created.
Right. Second, you have the difficulty. Third is the nonce.
Okay.
And fourth, crucially, is the Merkle root.
Wait, I want to pause here. Because words like difficulty and nonce sound incredibly abstract.
They do sound a bit like sci-fi jargon, yeah.
Let's break those down. What on earth is a nonce, and why does the network care about difficulty?
Well, this gets to the heart of how blocks are actually created, a process that's often called mining.
Right, crypto mining.
Exactly. The network doesn't just let anyone throw a box onto the pile whenever they feel like it.
That would be chaos.
Complete chaos. It demands that the person adding the box solves a cryptographic puzzle first.
Okay.
So the difficulty is essentially the network telling the computers, hey, here is how hard the puzzle is right now.
What kind of puzzle are we talking about here? Like Sudoku? Math equations?
It's essentially a massive guessing game.
A guessing game?
Yeah. The network requires the block's final identifier, its hash, to start with a certain number of zeros.
So track it.
Let's say the network demands a hash, starting with 5 zeros. Now, the data inside the block is fixed.
Right. The transactions are what they are.
Exactly. The timestamp is what it is. So if you run that data through the hashing algorithm, it gives you a specific hash. But maybe it doesn't start with 5 zeros.
So you're stuck. The block is invalid.
Unless you have a variable you are allowed to change.
Cool.
And that is the nonce.
The nonce?
Yeah, nonce stands for number used once. It is literally just a dummy number sitting in the header.
So how does it work in practice?
Well, the computer sets the nonce to 1. It hashes the whole block.
No zeros.
Right. It changes the nonce to 2, hashes it again.
Still no zeros. Oh, wow. So millions of computers around the world are just rapidly swapping out this dummy number, the nonce, over and over, trillions of times a second,
Yes.
just hoping to stumble upon the exact combination that spits out a hash starting with 5 zeros.
You've got it. That brute force guessing game is what we call proof of work.
Wow. And that requires massive amounts of electricity and computing power.
It does. The nonce proves you did the work. And the difficulty ensures that new blocks are only found every 10 minutes or so, no matter how many computers join the network.
That makes so much sense. It's like an artificial speed limit imposed by math.
Exactly.
Okay, so that covers timestamp, difficulty, and nonce. But you mentioned a fourth item in the header, the Merkle Root.
Yes, the Merkle root.
I am so stuck on this term. It sounds like a mystical tree from a fantasy novel. But reading the presentation, it's doing some incredibly heavy lifting.
Oh, it really is the anchor of the whole system.
Not so.
Well, the Merkle root is effectively a digital fingerprint that summarizes the entire block body.
Okay, summarize that for me.
Imagine you have thousands of transactions in the payload, right? Through a mathematical process called hashing, all of those transactions are churned and compressed down into a single, unique string of characters.
Just one string.
Yes. That single string is the Merkle root, and it gets stamped right onto the header.
Wait, I have to challenge this. You're telling me you can compress thousands of complex financial transactions into one tiny string of text?
Yep.
How is data not lost? I mean, can you just unzip a Merkle root and read the transactions?
That's a very common misconception.
Okay.
You aren't compressing a file like a zip folder where you can extract the original data later.
Now, what is it?
A cryptographic hash function is like a one-way meat grinder.
A meat grinder.
Yeah. You put data in, you turn the crank, and you get a fixed-length string of letters and numbers out.
And you can't reverse it.
Exactly. You cannot run the grinder backward to get the cow back.
That is a vivid image.
But, and this is the genius part, it is deterministic. If you put the exact same transactions into the grinder, you will get the exact same string out every single time.
Okay, so if I read a Merkle root on a header, I don't know what the specific transactions are.
Right.
But I know with absolute certainty that this specific fingerprint represents this exact batch of transactions.
Yes. And if we connect this to the bigger picture of cryptography, a hash function is extremely sensitive.
How sensitive?
Even the most microscopic change to the input data creates a wildly different output string.
So if I visualize this, The Merkle root acts like the tamper-evident seal on a medicine bottle.
Oh, I like that.
Right, because if a bad actor sneaks into the block's body and changes a single decimal point on one transaction, maybe to give themselves more money, the color of the seal on the outside, the fingerprint, changes completely.
It doesn't just change a little bit, it totally transforms.
That is brilliant. The metaphorical seal just shatters.
Exactly. And because the network only has to check that single Merkle root on the lightweight header, rather than reading all thousands of transactions in the heavy body, it detects the tampering instantly.
With almost zero computing effort.
Exactly right.
Okay, so now we understand a single block. We have our digital container, we have our heavy payload in the body, and we have our tamper-evident label on the header containing the timestamp, the difficulty, the nonce puzzle solver, and the Merkle root fingerprint.
That's the anatomy.
But the presentation isn't just how blocks work. It's how blocks and chains work.
Right.
So how do these isolated containers actually link up to form a continuous chain?
What's fascinating here is how simple but unbreakable the binding mechanism actually is.
Okay.
It relies on another piece of data in the header called the previous hash.
Let me guess. Every block holds the fingerprint of the block that came right before it.
Cryptographically holding hands, essentially. Let's look at a sequence. Say you have block 101. It goes through the mining process, gets verified, and its final unique fingerprint, its hash, is, let's just say, 4A2B.
Okay, 4A2B.
When the next block 102, is being assembled, it is forced to explicitly include 4A2B in its own header.
Under that previous hash category.
Exactly. Then block 103 will store the final hash of block 102.
It's like a chain of DNA. Each link absorbs a piece of the previous link.
Precisely.
But wait, this creates a logical loop.
How so?
If every single block has to point backward and store the fingerprint of a previous block, what happens at the very beginning of the timeline? There has to be a first block, right? What does it point to if there's absolutely nothing before it?
The architects of the system accounted for this. Every single blockchain begins with what is called the genesis block.
The genesis block, or block 0.
Right, block 0. Because it is the absolute beginning, it physically cannot have an earlier block to reference.
What's in the previous hash field?
By design, its previous hash field is uniquely hard-coded as a string of zeros, just literally 00000000000.
Wow.
It is the one and only block in the entire network that does not point backward.
It's the anchor in the bedrock.
It serves as the unmovable foundation for all subsequent data. Every single block that exists on that chain today can trace its lineage all the way back, link by link, checking previous hash to previous hash.
All the way back to that original genesis block.
Exactly.
Okay, let's put you, the listener, right in the middle of this. Let's talk about security and put you in the shoes of a hacker.
Let's do it.
You want to cheat the system. You decide you want to go back in time to block 99. You want to pry open the container, alter the transaction data to give yourself an extra 100 digital coins, and then close it back up.
A classic heist.
Right. Based on the plumbing we just outlined, what actually stops you from doing that?
What stops you is a concept called cascading failure.
Cascading failure.
Yeah. Let's walk through your scenario exactly as the math dictates. You go into block 99 and you change your balance.
Okay.
As we discussed with the Merkle root and the tamper-evident seal, the moment you alter that single decimal point, block 99's unique fingerprint, its hash, completely transforms.
Right. The seal shatters.
Exactly. Let's say its original valid hash was ABC, and because of your tampering, the new hash is XYZ.
Okay, I've successfully altered my balance, and my bad block 99 is now labeled XYZ. I just have to sneak it back onto the chain.
Well, here is where the trap snaps shut. Remember the cryptographic link?
The holding hands.
Right. Block 100 was already created, and inside its header, it is permanently looking for its parent, which was ABC.
Oh.
But ABC doesn't exist anymore. You changed it to XYZ.
Oh, I see. Because block 100 is looking for ABC and it sees XYZ, the physical link just snaps.
It snaps.
It essentially says, I don't recognize the block in front of me.
Exactly. The link physically breaks.
Yeah.
And it doesn't stop there.
What happens next?
Because block 100's header contains a pointer that is now invalid, block 100 itself becomes invalid.
Which means its own hash changes.
Yes, which means block 101 breaks.
Which means block 102 breaks.
Exactly. Tampering with one single transaction in an old block causes a cascading effect that instantly invalidates every single block that came after it.
It's not like pulling a brick out of a tower. It's a massive mathematical combination lock.
That's a great way to put it.
Right, if you force the first dial to a new number, it forcibly scrambles all the subsequent dials down the entire line permanently locking you out.
That is a much better analogy, and that mechanism is what creates immutability.
The power of permanent, unchangeable records.
Yes. The older a block gets, the more blocks are stacked on top of it. The presentation refers to this as confirmation depth.
Meaning the deeper it is buried in the chain, the safer it is from tampering.
Because if you, the hacker, alter block 99 and it's buried under 1,000 new blocks, you don't just have to recalculate the nonce puzzle for block 99.
Oh, right, the proof of work.
Exactly. To make the chain valid again, you have to possess enough raw computing power to recalculate the puzzles for block 100, 101, 102, all 1,000 subsequent blocks.
And you have to do it simultaneously.
Yes, before the rest of the network notices and adds a new valid block.
Which would require more computing power than exists on planet Earth.
Practically speaking, yes. It becomes computationally impossible to rewrite history.
And it's important to remember, getting a block into this chain in the first place is incredibly difficult.
Extremely.
The presentation has this blueprint for how a transaction actually reaches consensus and gets added, and it's a massive gauntlet.
Oh, it really is.
First, your transaction has to be broadcast to the entire network. Then it goes to a node. Then it gets bundled into a candidate block with other transactions.
And that's just the staging phase.
Right. Then comes the hurdle we discussed, the proof of work puzzle, or in some newer networks, a proof of stake process. Computers have to expend massive resources burning through those nonce numbers.
Doing the hard work.
And even after one computer finally solves the puzzle, they don't just get to append the block.
No, they don't.
They have to broadcast their newly solved block back out to the entire network.
Everyone checks their work.
Every other participant independently verifies that the math checks out, the signatures are valid, and the hashes link up. Only when the majority agrees is it appended to the local chain.
It's strict.
The gauntlet a piece of data have to run just to get welded into this container yard is staggering.
It is a gauntlet entirely by design, though.
Yeah.
The integrity of the entire system relies on both that cryptographic hash pointer tying the history together and this distributed consensus process, ensuring everyone agrees on the present.
So what does this all mean for you listening? We've talked about hashes and nonces, Merkle roots, and cascading failures. But if you're sitting in a boardroom, managing a supply chain, or just trying to navigate the modern digital economy, why does knowing the plumbing of a blockchain actually matter?
It matters because this architecture fundamentally redefines trust.
Okay, redefine trust for me.
Well, the presentation outlines 3 practical pillars that emerge from this highly technical plumbing: transparency, trust, and security.
Let's unpack those. Transparency first.
Sure. In a traditional financial system, the ledger is a black box.
Right.
The central bank sees it, you don't. You have to trust their reports. But with a public blockchain, everyone can verify the ledger independently.
Because everyone has a copy.
Exactly. Because of the way the blocks link and the hashes broadcast any tampering, there are no hidden records.
Yeah.
The entire history is mathematically visible to all participants at all times.
Which leads directly to the second pillar, trust. I was thinking about this while prepping for today. It is incredibly liberating to realize that trust in this ecosystem isn't based on a corporation's promise.
Not at all.
It's not based on hoping the central bank or a third-party intermediary doesn't make a mistake or act corruptly or freeze your account.
You are trusting the math. You are trusting the cryptographic links and the consensus gauntlet.
Yeah.
Secure transactions can happen peer-to-peer across the globe without needing that traditional middleman to vouch for the exchange. The protocol itself is the middleman.
And the final pillar is security.
Which is the direct result of that confirmation depth and immutability we explored.
Right.
It provides robust, near unbreakable protection for the transfer of digital assets because it creates a permanent chronological history.
Once it's locked, it's locked.
Once the container is locked, the puzzle is solved, and it is buried under a few new blocks. No hacker, no rogue CEO, no government entity can reach in and quietly alter the past.
That is a profound shift in how human beings handle data.
It really is.
Let's do a rapid-fire recap for you listening, just to lock all of these mechanics in.
Let's do it.
We started with the block, a digital container that holds verified transactions. To solve the problem of overwhelming data, it's split into a lightweight header for metadata and a heavy body for the payload.
And we examine the header's components, the timestamp, the difficulty, the nonce that acts as the puzzle solver, and the Merkle root.
Which acts as that tamper-proof fingerprint summarizing the entire body.
Exactly. We also looked at how the chain is forged. Every block stores the previous hash of the block before it.
cryptographically holding hands.
creating an unbreakable cascading chain all the way back to the foundation, the Genesis block, block 0.
And we saw how that combination lock structure creates true immutability, ensuring that history can only be added to, never edited or deleted, because the computational power required to recalculate the cascading hashes is virtually impossible to achieve.
It's an airtight system.
It really is. Now, according to the source material, the logical next step for future exploration is diving even deeper into consensus mechanisms.
Oh, that's a huge topic.
Yeah, really dissecting the difference between how proof of work burns electricity to find that nonce versus how newer proof-of-stake models secure the network using capital. But that is a deep dive for another day.
It is. But before we wrap up, the mechanics we've discussed today raise an important question.
What's that?
Something you should ponder as this technology continues to integrate into mainstream systems. If we connect this plumbing to the bigger picture of our lives, if the absolute unbreakable rule of blockchain technology is that it only adds history and never edits or deletes it, how will a purely blockchain-based digital society handle the human desire and sometimes the legal right to be forgotten?
Wow. That is a heavy thought to end on. Because if everything is an immutable combination lock, there is no erasing the clipboard, no fresh starts.
Exactly.
Think about that the next time you picture that massive container yard. The containers aren't just securing themselves. They are welding themselves into a digital monument that lasts forever.
Forever is a long time.
It certainly is. Thank you for joining us on this deep dive. Keep questioning the plumbing, and we'll catch you next time.